All right, let's get straight to it. System performance really boils down to two key forces that are often at odds: latency and throughput. Think of it as speed versus capacity. In this explainer, we're going to break down the core mechanics of both.
Okay, here's our roadmap. We'll start with the basic definitions, then break down the anatomy of performance. After that, we'll dive into Little's Law, look at the saturation curve, check out some optimization patterns, and wrap it all up with a direct comparison.
First up, core definitions. This is all about understanding the speed of one thing versus the volume of many things. So what is latency? It's all about speed. It's simply the time it takes for a single request to go out and for the response to come back. We're measuring time here, usually in milliseconds. Throughput, on the other hand, is all about capacity. It's not about how fast one thing is, but how many things your system can handle in a given period. This is a rate, right? We measure it in things like requests per second. You know, the classic water pipe analogy is perfect for this. Think of latency as the speed of a single drop of water traveling through that pipe. Throughput, that's the total volume of water flowing out, the gallons per minute. You can have a really fast drop, which is low latency, but if the pipe is tiny, you're still going to have low throughput. And this is super important. High latency and high throughput can absolutely exist together. The perfect example is shipping a hard drive with FedEx. The latency is terrible, right? It's like 24 hours. But the throughput is massive. We're talking terabytes per day, which is way more than your internet connection can handle. This proves they are independent variables. Okay, moving on to section 2, the anatomy of performance. Here's the thing. Latency isn't just one single number. It's actually made up of a few different parts. And if you want to improve it, you've got to know which part is the problem. So the total latency for any given request is really the sum of three things: propagation time, queuing time, and processing time. Basically, how long it takes to travel, how long it waits in line, and how long it's actually being worked on. Let's break that down. Propagation is just physics, the time it takes for data to travel, limited by the speed of light. Processing is the actual work your CPU is doing on the request. But the real killer, the one you really have to watch out for, is queuing. That's the time a request just sits there, waiting in a buffer because the system is busy. When your system is under load, this queuing delay is almost always the culprit for slowdown. Now, throughput is a different beast. It's always, and I mean always, limited by whatever your scarcest resource is. Is your network card maxed out? You're network bound. Is your CPU pegged at 100%? You're CPU bound. Constantly waiting on the disk or database? That's I/O bound. Your system can only ever be as fast as its slowest part. All right, section 3, Little's Law. This is where things get really interesting. It's a fundamental formula from queuing theory that ties latency and throughput together, and it's absolutely essential for capacity planning. The formula itself is pretty simple. L equals lambda W. Here, L is for concurrency. That's the number of requests actively being handled by your system. Lambda represents throughput, or the rate of new requests coming in, and W stands for latency, which is the total time a request spends inside the system. Let's make this real. Imagine you want to handle 1,000 requests per second, and your average latency is half a second. Little's Law tells you that you need to be able to handle 500 concurrent connections. It's just 1,000 times 0.5. If your system can't handle 500 active connections at once, there's just no way you're going to hit that throughput goal. It's that simple. Okay, section 4, the saturation curve. This is crucial because the relationship between load and performance isn't a straight line. It's not linear at all. This curve shows you exactly how systems break down when the pressure gets too high. You can think of a system's performance in 3 distinct zones. First, there's the linear zone. At low traffic levels, everything's fine, latency is stable and flat. Then, as traffic ramps up, you hit what's called the knee. This is where resources start to get tight, and you'll see latency begin to creep up. And finally, you hit the saturation point. That's when some critical resource is at 100% utilization. And when you hit that saturation point, 2 things happen. First, your throughput completely plateaus. It just can't go any higher. And second, your latency goes vertical. It skyrockets because every new request is just getting piled up in a queue, waiting. This is the performance wall you absolutely have to design your systems to avoid. So that brings us to section 5, architectural optimization patterns. Knowing all this, you have to make a choice. What is your primary goal? Are you optimizing for latency, for speed, or are you optimizing for throughput, for volume? If you're optimizing for latency, your goal is to make every single request faster.
This means using techniques like caching with Redis or Memcached to avoid slow database calls. You'd use a CDN to get your content closer to users, which cuts down that propagation delay. You'd use connection pooling to skip the overhead of setting up new connections. And you might even denormalize your data to get rid of expensive database joins. But if you're optimizing for throughput, you're playing a different game. You're focused on total system capacity. This is where things like batching come in. Instead of 100 separate database writes, you group them into a single transaction. It means using asynchronous I/O, like you see in Node.js or Nginx, so your workers aren't just sitting around blocked and waiting. And it often involves message queues, like Kafka or RabbitMQ, which act as a shock absorber for traffic spikes, letting you process the work at a steady pace.
Okay, let's wrap this up with our final section, a direct, side-by-side comparison.
So let's just run through this table to lock in the concepts. The primary focus for latency is the speed of one task. For throughput, it's the capacity of the whole system. Latency is absolutely critical for things like online gaming, high-frequency trading, or search results. Throughput, on the other hand, is what matters for big file uploads or data analytics pipelines. For metrics, with latency, you're looking at percentiles, like your P95 or P99 response times. With throughput, it's just a raw rate, requests per second. And finally, the bottlenecks are different. Latency is often hit by things like network distance or just plain inefficient code. Throughput usually slams into a hard physical limit like your CPU cores or your disk I/O.
So, now you know the mechanics. The key takeaway is that you have to know which problem you're actually solving. Take a look at your own system. What's the real bottleneck? Is it latency or is it throughput? Are you trying to make one thing faster or are you trying to do more things at once? The answer dictates your entire approach.